who should be using Alias, and how can people get started?
Alias is typically used by people doing design work. It's used in conceptual modeling and production Class A surfacing. It's a free learning edition, so anyone can learn it. There's a lot of material that we have when you install it as a free trial. Happy for you to use YouTube or anything like that, where we've posted a bunch of videos on learning Alias.
How much training data do GNNs typically require for CFD?
It's really hard to put out a number because it depends a bit. What do you want to do with your car? If you just want to change the roof height, then you can easily get away with, let's say, 10 samples.
Ladies and gentlemen, today with another super exciting session with Autodesk, where we'll present how multiple disciplines can leverage a single source of truth in Alias. Live referencing to VRED enables users to create high-end visualizations, while the use of geometric deep learning with NavPack unlocks real-time engineering insights in the design process. And I'm super excited to have Barry and Jakob from Autodesk today in the deep dive session. Without further ado, guys, I'm super excited. Let's get started.
Thanks, Joseph. I'll take over. At Autodesk, we want to enable our customers to build better cars faster. And there are two aspects of building better cars faster. The first aspect is really faster. So the automotive OEMs are under a lot of pressure to really shorten the time to market and the development times. I think basically every OEM really wants to bring out new models in a shorter amount of time. But that's not the only aspect. The second aspect is that especially with the rise of electric vehicles, the aerodynamic performance becomes increasingly important because it directly affects the electric range of the vehicle. Right. So if we want to achieve those goals, we are really convinced that the best way to achieve those goals is to provide additional functionality, additional values in the tools that actually do the job. And if it comes to automotive design, this is most of the time Alias, where people really do the surfacing of a car. If it comes to high-end visualization, people use VRED to really do the storytelling, evaluate different design stages. And what we did in the past is to connect both tools via live referencing. And now what additional comes into the play is that you can not only connect to visualization, you can also connect to engineering, bring engineering insights in the design process by the use of NavPack, which uses geometric deep learning to store aerodynamic knowledge and make it available in the design process. And this is also where we want to focus on today's webinar, a bit on the connect to engineering side. So the underlying idea is really that you have one single source of truth, one design model in Alias, and you can quickly connect to different disciplines, either via live referencing or the usage of AI. And the underlying vision is that people can really do what we would call interactive design. So they can really meet in one room and make decisions in that room based on actual data. They don't have to give away their current state of work, their current design model to other departments and then wait for results, wait for the next weekly meeting, and then meet again, make a decision or postpone the decision because results are simply not present. That's something that is very time consuming and also very costly. So imagine you have all those different disciplines together in a collaborative workflow and can make decisions basically in real time. And in terms of the Navasto integration in Alias, this works in a way that the NavPack software enables customers to train their own AI models based on their own simulation data. So basically, they use data that was produced in the past and extract the information that is inside those data sets. And instead of simply deleting those data sets because they require a large amount of disk space, which is really huge, they store this knowledge in an AI model. Once the AI model is properly trained, it then can be used. So every time a designer or a surface modeler comes in with a new input, a new geometry, a new car, he can leverage the existing AI model to produce results in real time. And this is really a big step ahead, because you have to imagine in the present state, if people require high fidelity simulations to provide them with the results, this can take days or even weeks until the result is back on the designer's table. And I mean, you basically have no knowledge about the aerodynamic performance while you're designing for days or weeks, which is basically something that is not good for a faster time to market. Right. So that's the underlying idea. If you think about the whole process, it basically consists of 3 steps. The first step is you need to read and process your existing simulation data. Step number 1, which can take a bit of time. Second step is you then use that data to train and update your AI model, which can also take a bit of time. At the end, you save the AI model as a container file on your disk, which you then can use in Alias, which is quite fast. Right. So the first 2 steps, they are basically performed in NavPack, while the third step is performed in Alias. Right. And without further review, over to Barry. Barry, can you take?
It's not allowing me to share right now. There it goes. Just taking it a second to get going. Okay, so this is an example, I suppose, as Jakob said. I'm currently, I have NavPack Design open, plugin for Alias. It's found under the Evaluate tab in Alias. I've got a car model loaded. Jakob has taken the time to run the simulations and create a container file. So I'm connected to that container file here. It's fairly straightforward. You simply select your model and ask for a prediction. So the system is going out, looking at the container file and all of the simulations. It's going to return a result to me with some analysis, some aero analysis on this model. And here we can see that analysis. So I think as a surface modeler, which is my background just in surface design and automotive design versus the engineering side, I have to be a little careful with how I interpret these results. I need, let's say, a professional that knows exactly what these numbers mean. Some things that I have learned in my experience so far is the coefficient of drag is quite important. Most vehicles will have some kind of a target there. And we can see here some predictions and all of the numbers for downforce on the front and rear axles, things like that. Something that many people like to understand about vehicle designs is their frontal area. So you can compute that frontal area. In this case, it gives us meters squared in the frontal area. Some other things that we have to explore here, just some different ways to display the analysis, just different maps. We're not changing what the analysis is. We're just looking at it in some different colors. We have some different attributes that we can look at here. Currently, we're looking at the mean. We can also look at what I believe is standard deviation. And then we can look at our calibrated uncertainty. So if we start to explore a couple of different models here, in this case, I've got maybe a different designer. You know, you'll have this design, and then maybe engineering comes and says, well, there's not quite enough headroom in the back. So we could get a different design, maybe here, where we get a bit more roof space in the back, a little more packaging for the passengers. We could then take this brand new design model and simply pick it and ask for a prediction based on this. Again, it goes off, you know, a minute or two. This is just running for me. I'm just running on a pretty basic Dell laptop here, so no special GPUs, no special render farm, you know, thing hooked in the background. It's just a pretty basic Dell P1 laptop, and I again get the results here. So we can see here the coefficient of drag has gone up a touch. We can, again, simply compute that frontal area. I didn't write down the result before, but I think it was 2.22 maybe meters square, something like that. And then again, we can come in here and we can look at our standard deviation and then maybe our calibrated uncertainty. Now the calibrated uncertainty it's kind of a interesting thing to look at for users. This just is your indication that your model has not fallen outside of the aerodynamic area that's been concentrated on. And I'm using some generalized terms just as a surface modeler. I'm sure Jakob could explain these in more detail, but I couldn't put a very tiny passenger car into this aero and analyze it against this aero container. This aero container is designed for this size and proportion of vehicle specifically. So there's been quite a few aerodynamic runs done on this, and I'm using those to simulate the predictions on this model. So here it shows still within pretty good area of uncertainty, and you can just continue to iterate on your design and get better and different results. So I'm going to switch now. This model tends to have what I would call a fairly narrow greenhouse with a pretty wide shoulder area here. So I'm just going to switch to maybe a little bit different design model here that's got a little bit wider volume across here, a little bit narrower shoulder, and we're going to do some predictions based on this. I know that wheels were not in the previous aero simulation, so I'm going to just take the wheels out. Again, I've got this just shaded here, and you just box select. It grabs that shading or that tessellation and sends it to the NavPack tool to do its prediction. So give it just a short time here to get these results returned. Again, running on a fairly small laptop here. So in this case, I can again do the compute frontal area, and we'll see what we have here. My guess is 2.4. So we've definitely gone up in frontal area, right? And that is because we've widened this entire greenhouse. And then we can go to our calibrated uncertainty, and you can kind of see here where the calibrated uncertainty starts to turn a little bit red. And this should be a bit of a cause as a surface designer. This is where I think you might get some information that's useful more to a surface designer, that you might want to be careful with these results. Talk to your aero support personnel, engineers, I guess we'd call them. In this case, you can see here, this mirror is pretty much bright red. This means there was probably no mirror included in the original. And in this greenhouse, we've got quite a bit of red area. And if I just showed you kind of maybe why that's happening, if we go back here in Alias, we can turn on the other model in the background. And if you look here, in light green is where the previous model was. So we've grown probably 50 or 60 millimeters in width. And you can just see that in the back, we've changed quite a bit. So we may have gotten outside of the workable area for our aero results. And we may have to have the aerodynamic engineers update our container file so we can get a little bit better results from that. I think maybe the last thing I might want to show is how you could take then this model and drive it into using our live referencing. So we have our live referencing here, and you can live reference this file into VRED, and then you've got, you can start to turn on some fancier bells and whistles in here using any number of the tools in VRED. So I think connecting the VRED tool, the Alias tool, and the aerodynamic tools together allow you to get quite a few apps linked together so that you can do both design, visualization, and engineering, all pretty streamlined workflow. So with that, I think I may pass it back to Jakob.
Thanks, Barry.
For a little.
Let me take over again. And I'm very happy that you brought that up, that this is not a magic stick. There will be no miracles here. That it's really an engineering tool. It requires best practice. It needs some form of consistency between what you use to train that model and how you want to use that model. So there are a few things that this technology really is. It's a possibility to left shift high fidelity simulation data. As I said, basically you run all those simulations on an HPC cluster or wherever when the project is not hot yet, basically. And then you store the information that is in those simulation samples in the AI model. That's called left shifting in the industry. If you use that buzzword, and then you can use the AI model. So you gain a lot of speed, but at the cost of generalization. I mean, as you saw, our AI model did not knew about car models with a let's say classic side mirror. That was never seen by the model, so it did not know about this. This is why they turned up red in the calibrated uncertainty. The model only knew about those fancy camera systems that you see on electric cars these days. Right. So this is really important. So it will never be a complete replacement for solvers that really solve partial differential equations, because you basically consume simulation data. So those high fidelity solvers like a CFD solver or an FEA solver, they produce the data that is used for the AI model training. Right. It's important also to mention that this is a purely data-driven method. So basically, it does not care whether it predicts a pressure on the surface of a car, a wall shear stress, a temperature, a von Mises stress, or displacement. It's purely data-driven. So you can apply this to different applications. External aerodynamics, as you saw, I think this is a massive use case, since you really can boil down the turnaround time for an aerodynamic evaluation from 2 weeks to, let's say, 10 seconds on a standard laptop in a meeting room. You can also apply this to passenger safety or crash analysis, durability or structural analysis, or even to the cost of sheet metal stamping. These are applications that we see in the field. And as I said, it's the same technology. It's about inputs and outputs. So you store the corresponding simulation results in the AI model and then make it available in a tool where you also get also produce the inputs. Right. So the one question that we usually get is, how accurate can this get? And also, how many samples, how many data samples do I need to feed into the model until it gets accurate? So if we talk about accuracy, maybe let's go back again to external aerodynamics and have a look at these plots. So what you see in this plot is really the comparison between an AI result and a simulation result, a CFD result, in terms of the aerodynamic drag of that vehicle. So basically everything that is on the diagonal line would be a perfect result. And every scatter dot that you see in this diagram is basically an unseen geometry variation of this research sedan here. This is a driver model, so-called driver model. It's a mix of a BMW 3 Series and an Audi A4. And we did a lot of variations, and all the unseen geometry predictions that were not seen during the AI model training. And that's an important fact. If you want to evaluate the quality of an AI model, they got predicted here for that plot. So you see, not everything is on the diagonal line, because already in the simulation parts, you have like some kind of noise, and you cannot overcome that noise. So I usually say everything that is within 3 drag counts is a very reasonable result. And I think it's very important that the AI model predictions are reliable. So the trend is always in the right direction, and you get an information whether you can trust the prediction or not. Right. It's not limited to scalar values. As you saw, you can predict values on the surface of the car, which is usually a pressure, static pressure, or a wall shear stress. But you can also predict volume field information, as we did here with those slices in the wake of the car. And if you again compare the simulation result, the CFD result, which counts as a ground truth these days, with the AI prediction, you see that again for different geometry variations, they are very similar. They are not exactly the same, but they show exactly the same patterns. They show exactly the same trend. And I think this is what makes the technology valuable, since the AI prediction, again, only takes a few seconds. Right. You can also, if you're more like on the engineering side and want to look a bit closer into vertical structures, you can also use the so-called in-plane velocities and visualize them. And I think you make the same observation. The general trend is observed quite well, while smaller details might differ a bit. Right. So let's imagine one thing. You got the system running. You used all your simulations, whether this is like a fresh set of simulations or it's the legacy data that is present in your company or in your project. You use that, you trained your AI model based on that data. You made it available in Alias. You could play around with different parts, different shapes, and you could evaluate the performance. However, you're not quite satisfied. Say like, yeah, the aerodynamic resistance or the drag is still too high. Electric range of my vehicle is not competitive. I need some guidance how to really gain some performance gains somewhere. How can I do this? And this is something where we can also couple this predictive AI model that you saw in the previous slides and also in Alias with a generative AI model, if you want to do it like this. So basically the generative AI model direction creates unlimited new variations of that car completely automatically, completely new unseen geometries. And for each of those new geometries, you also get a prediction again from your AI model. And if you put those two puzzle pieces in a loop, couple them with an optimizer, you can run very quick optimizations, as we did here with the vehicle drag of that SUV, where you see we roughly evaluated the drag for 100 new geometries, coupled this to an optimizer. So every dot that you see here corresponds to a geometry and to an aerodynamic result. And basically you can just pick. Let's imagine you had like this very large and high greenhouse, which was like in a drag value somewhere here. And then you can basically pick each of those points that fits your objectives and your constraints, also looks good, last but not least, and just choose what you want to do. You can either just follow the AI guidance, trust the prediction. You can also say, no, I would never trust an AI prediction. I want to run a test simulation for the most promising geometry. I run the simulation, I evaluate, and if it's proven, then I can go into this direction. Maybe I just want to use the 5 promising variants and not 100 of them. I think that's the power. And maybe to wrap this up, this technology, this deep learning technology, should be really used as a recommendation system or as a pre-selection system, which helps you to get a bit more confidence to follow those ideas. Because I mean, every change on that vehicle, if you have a high fidelity model, really requires some effort, some hours of modeling to really make it crisp and shiny. So this hopefully helps you to get some confidence in that. Right, that was the last slide. Probably there are some questions from people in the internet, from the audience. So I'm happy to answer them.
Super nice. Thanks, Barry and Jakob. Let's head over to the questions. We have a couple of them, actually. One question, could you please specify again what this surface uncertainty is?
Right. I can take this question. And yeah, again, I'm very happy that Barry brought this up because I think it's very important. If you think about the fact that an AI model always gives you a prediction, you feed in a new input, you get a prediction, and then what now? The most important question, and I would say that's kind of the holy grail of machine learning, is to get an idea whether you can trust a prediction or not. And there are many ways out there. What we said is we really want to provide a value where a designer has information what detail, what part of the car makes a prediction not trustworthy. Because only information, you should not trust this prediction, is a bit of a weak information. So we said like, okay, Barry, keep in mind your AI model has never seen mirrors. We didn't do that for the last 2 years, so keep in mind, if you remove the mirrors, you're back in range. And I would basically say it defines like what's within the range of the AI model and what's completely outside. And that applies for all machine learning and AI models, that they are good at interpolating things and they are very bad at extrapolating.
I think that covers it. I think a very interesting question is always, how much training data do GNNs typically require for CFD?
Right. I like that question, although it's hard to answer. It's really hard to put out a number because, of course, it depends a bit. What do you want to do with your car? If you just want to change the roof height, then you can easily get away with, let's say, 10 samples. If you really want to apply smaller changes to radius changes on the mirrors and lots of changes on a highly sophisticated car geometry, then you can easily consume up to thousands of samples.
Then we have what kind of CFD data can be used to train GNNs? Probably going back to maybe mesh-based connectivity, I would assume.
Good question. I mean, usually I would say, if we think about different fidelity levels, so you have cheaper run simulations that run faster, need like lower amounts of hardware resources, and then you have very expensive transient DDS simulations. I mean, of course, I would say if you have the data, use as high fidelity simulation data as possible for the AI model, but there is no limitation. You could use a simple potential solver and just feed in that data. But the question is, what's actually the delta, since those solvers are also very, very fast. But I think in the case of the automotive OEMs, it's really high fidelity data that usually is used for something like this.
Can GNNs handle transient CFD?
In theory, yes, they can. But if you can use transient CFD and just calculate average values at the end, an average drag, average pressure distribution, whatever you think, and feed this in a GNN. But then you don't get a transient prediction. If you want to get a full transient prediction, then what you need to do is basically, it's called a rollout model. So you predict time step number 1 and use the predicted time step number 1 as input for the prediction of time step number 2. That's possible. However, it's very, very expensive in a computational sense. So I've never seen that in the field, fully transient.
We have another question. Does the optimization modify the actual geometry?
Yes, it does. But it doesn't do it like on a NURBS or subd level. It uses a mesh and then predicts new meshes.
Precise answer. I like that. How much training on the specific problem do you need to be accurate enough? For new problems, how does the training requirement compare to just iterating through simulations with an optimization algorithm? A pretty long question. Should I split it maybe, or did you?
No, I think I get it. And I think it's a both ways are valid, I think. I mean, you can apply an optimization algorithm to a simulation workflow and then iterate. That's something we've done before. I think like almost 10 years ago, we also implemented such workflows for customers. However, you need to keep in mind, I mean, if you if you think about this picture of people from different departments sitting together in a room and wanting to make some actual decisions in that room, and then you start a process like this will take time. This will take, let's say, like at least a night or maybe two, depending a bit on the problem and what you really want to do. Where else you need to keep in mind, if you use the technology we presented today, you have the possibility to really train on legacy data. And that's what we hear from customers. I mean, it's maybe their like fourth or fifth car program, and they did stuff like this before. There are tons of data. So the knowledge, what happens if you change that feature of a car or that tiny little bit, that is present in the company. And with a technology like this, you make it available inside the meeting room, within the meeting, without having to postpone like to a week later or whatever.
Someone wants just some clarification to summarize. Surface uncertainty equals locations which may be corrupting the predictions, correct?
You can frame it like this. Yeah, it's like an out of distribution indicator.
Maybe a question from my side, Jakob. You mentioned that GNNs are very good at interpolating, but bad at extrapolating, right? So how do you deal with edge cases? So basically you train on a large amount of data, whatever large means in this case, right? How would you actually handle edge cases, for example? Would that be then another training point for that acts as an input, or how do you handle edge cases? Or maybe unseen scenarios?
Right. I mean, if we talk about the unseen scenario, it depends a bit. Is this like within range? Or like, let me phrase it a bit different. Has the model seen something similar before? Not exactly that, of course, but maybe something similar or not. And I think if you really want to use this in production, you need to be honest and rather be a bit too conservative with the edge case. So if it's questionable, I would rather advise to talk to the aerodynamic engineer and run an actual CFD simulation.
That makes sense.
But what you can do to really push the boundaries is, of course, like, I mean, you can use your legacy data and you can also augment it with some, let's call it artificial legacy data, where you just have like a larger bounce. And I mean, usually people know a bit what's possible in the company and what's not, what fit on the street.
And if they don't, they can reach out to Jakob, right?
Always. Rather on Barry, how to really make it happen.
Sounds good. Last question before I wrap it up, which is about some typical pitfalls when training GNNs for CFD data.
All right. I would say that there are two things. First is the data set. So it's really important to analyze the data set. What are the distributions? Do I just have one car with the mirrors and 1,000 cars without a mirror, and I just want to do some predictions with mirrors? That's like just a one hot encoded distribution. That's not good. So machine learning models, AI models, they like good distributions. That's the first thing. So make sure it's really a sufficient data set. If it's not from scratch, then maybe think about augmentation. Add some samples that create a good distribution. Think about, what do I want to do with the model? That's usually the best question if you answer that, then usually your data set will also be sufficient. That's step number one. Step number two is, such a GNN has lots of hyperparameters. So I would always highly recommend running a model selection and find the right hyperparameters that do the job for this particular data set. So that there are multiple ways how you can like create a graph neural network, multiple architectures. But my vision, and this is also how we implemented that in NavPack, is that the graph neural network adapts to the use case. I think that's quite important.
That covers it. I want to also give Barry a question, like, who is Alias for? Like, who should be using Alias and how can people get started?
Alias is typically used by people doing design work. So it's used in every major OEM in the world, I believe. I don't know of ones that are not using it. It's used in conceptual modeling and production Class A surfacing. There's a free learning edition, so anyone can learn it. There's a lot of material that we have when you install it as a free trial. So happy for you to use YouTube or anything like that, where we've posted a bunch of videos on learning Alias.
Sounds good. I've posted also some links in the live session so people can check it out. Barry and Jakob, thank you so much for this live session. I also learned a lot again. So really exciting to see what people will be doing out of this deep dive and reaching out to you guys. Thanks again, and I'll see you hopefully in a second episode in the future.